Hi, my name is Dennis Angel. I am an XRPL core developer for XRPL Labs, and today we're going to be discussing cryptography. Okay, so first we're going to go over the agenda. We're going to be talking about key management, random number generation, hashing, encoding and decoding, signing and verification, verification in detail, secure memory handling, and cryptographic handshakes. So let's get started. First concept is key management. Key management refers to the process and mechanisms used to generate, distribute, store, and revoke cryptographic keys. Why do we need this? Keys are the foundation of cryptographic security. If keys are compromised, the security of the entire system collapses. So proper key management ensures that only authorized parties can access and use the keys, and that keys are changed or destroyed when no longer needed. Some of the concepts here, key generation is creating strong, unpredictable keys. The key distribution is securely sharing these keys between parties. Key storage, protecting keys from unauthorized access. Key rotation refers to regularly updating the keys and limiting exposure. And then key revocation provides for invalidating keys that are no longer secure. The next section is random number generation. So random numbers are very important, and this is the process of producing numbers that are unpredictable and lack discernible pattern. So why is this necessary? Because cryptographic systems rely on randomness for key generation, initialization of vectors, nonces, and other. Weak or predictable randomness can lead to vulnerabilities, making it easier for attackers to guess keys or other secret values. Key concepts, true randomness is derived from physical processes. You have pseudo-randomness, which is generated algorithmically, but should be unpredictable if seeded correctly. And then entropy is a measure of unpredictable randomness. The next section is hashing. A hash is a function to take an input or message and produce a fixed size string of bytes, typically what we refer to as a digest, and is random. Why is hashing important? Hashing is used to verify data integrity, store passwords securely, and is the building block of cryptographic protocols. A good hash function is deterministic, fast, and produces outputs that are infeasible to reverse or find collisions. Some of the key concepts, obviously, as we said, deterministic. The same input always yields the same output. What we refer to as pre-image resistance. So it's hard to find an input that hashes to a given output. Collision resistance. It's hard to find two inputs with the same output. And then what we call the avalanche effect, which is small changes in the input produces a very different output. So the next section is encoding and decoding. Encoding transforms data into a different format using a scheme that is publicly known, while decoding reverses this process. Why do we do this? Encoding is not encryption. It is used to ensure that data can be safely transmitted or stored. It does not provide confidentiality, but it ensures compatibility and integrity between the transport. Some key concepts here. We have two different types, base 64 and hexadecimal, and then again, there's no security guarantee with hashing. The next section is signing and verifying. So digital signing is the process of using a private key to create a unique signature for the message. Verification uses the corresponding public key to confirm the signature's identity. Why do we do this? Signing provides authenticity, integrity, and non-repudiation. Some of the key concepts, the private key is used to create the signature and should be kept secret. The public key is used to verify the message and can be shared. And then the signature is a unique value derived from the message and the private key. And the verification step confirms that the signature matches the message and the private key. So we'll go into verification in detail. The verification is, again, the process of checking the signature is valid for a given message and public key. It ensures that the message was indeed signed by the holder of the private key and that the message has not been tampered with. The next section is secure memory handling. So secure memory handling involves protecting sensitive data like keys and passwords in memory from unauthorized access or leakage. Even if a cryptographic algorithm is strong, poor handling of secrets in memory can lead to compromise. So attackers may exploit memory dumps, swap files, or other vulnerabilities to extract secrets. Some key concepts here. It's called zeroization, which is overriding the memory after to prevent data remnants. Access controls, restricting who or what can access sensitive memory. And isolation, keeping sensitive data separate from less secure parts of the system. And then finally, we have cryptographic handshakes. So a cryptographic handshake is a process by which two parties establish a secure communication channel, often negotiating keys and verifying each other's identities. Why do we do this? Handshakes ensure that both parties agree on cryptographic parameters and the communication is protected from eavesdropping. In summary, cryptography is a multifaceted discipline that secures digital communications and data. Its effectiveness depends not just on strong algorithms, but on careful management of keys, the use of true randomness, and the integrity of hash functions. The proper handling of sensitive data and robust protocols for ensuring trust and secure channels. Signing and verification are central for ensuring authenticity and integrity, while secure handshakes and memory handling protect against a wide range of attacks. Thank you.